Hello, class. Welcome back. This is lecture 9. Today we're talking about linear independence and nth order linear homogeneous equations with constant coefficients, probably the longest title that we'll ever see. So it's really just two parts. So the first part is about linear independence. So remember that last time we learned about linear dependence. So this time it is linear independence, which is sort of like the opposite notion. So let's just jump right into it. So last time we talked about like a whole bunch of functions together having this property of linear dependence. So now we're talking about a big list of functions, f1, f2, up to fn, having a property again, but they are called linearly independent instead of dependent if, so it's the opposite of dependence. So dependence was if there were some constants that do something. So linear independence is if there does not exist such constants. So there does not exist any choice of constants. So one for each function. So there's also going to be n of them, such that, so the idea last time was things were dependent if there was some way to make a combination of them equal 0. So independent is saying that that's impossible. They're independent if that cannot be done. And that's what this is saying. So functions are linearly independent if there's no way to make a combination of them be 0 besides the very boring choice, which is you just cheat and you just say, yeah, I'll make all the constants be 0. If there's no other way to do it, then they're called linearly independent. So in other words, the only way to make 0 is out of these functions is the easy, cheap way. Okay, so let's see an example of 2 at a time for now. So of course, for 2 functions, it's really the same as being multiples of each other, though sometimes this is a bit harder to see than it seems at first. Okay, so these are linearly independent, and what that really means for 2 functions is that they're not multiples of each other, but we want to use our fancy new definition instead. Think about it that way. So to show that they're linearly independent means I got to try to build 0 as a linear combination. So I got to try to find 2 constants where I can say that this equals 0. Oops, plus. But then it's going to turn out that C1 and C2 just have to be 0. There's no other way to make this equation be true. So how can we do that? Well, let's just plug f of x and g of x in. So what we're doing is we're saying that this needs to always be 0, needs to equal 0. So what we're really saying is for any choice of x, this should always equal 0. And if I could find 2 constants that make this happen without cheating, without picking the easy ones, that means they're linearly dependent. If I can't, that means they're linearly independent instead. But what we're going to do is we're going to use that this has to always work for any x, and so pick a couple x's. So if x equals 1, well, first of all, I can factor out x squared to make things look a little bit easier. And if I want this to always be 0, that means I need to now focus on this factor being 0. So if x equals 1, I'm going to get that C1 equals negative C2 by plugging in 1 there. But if x equals negative 1, I'm going to get C1 equals C2 because I'm going to get C1 minus C2 equals 0. So then what I know about my two constants, so what I'm doing is I'm using values of x to figure out my constants, what they have to be to make everything work. So now I know that C1 equals negative C2 equals C2. Well, there's only one number that obeys this property. That equals its own negative. Its own negative. And that number would be 0. But then now I know C1 equals C2. So C1 equals 0 too. So I've shown independence because I've shown that the only way to make 0 is if both constants are 0. There's no other sneaky way to do it. So they're independent. Okay. You could do the same trick with other functions, sine of x and cosine of x. So this one's a little bit trickier to see because sine and cosine are very similar. So you might think that they're similar enough to be dependent. Like x cubed and x squared are more clear that they're independent of each other. They're not multiples of each other, but sine and cosine, a little bit more unclear, but they are also linearly dependent. And we can show it in the same way. So you suppose that there are some constants such that you can build 0 as a linear combination of the two functions. So this time sine and cosine. And then I'd show by plugging in x's that this is the only choice, that there's no other way to build 0. That the old boring way of just making both constants be 0. So again, the point is that this equation I'm saying needs to always be true for any x. So I can just plug in some clever x's. So if x equals 0, then I'll get C1 times 0 plus C2 times 1, because cosine of 0 is 1 and sine of 0 is 0. So this will tell me C2 equals 0. And if x is, let's do pi over 2, I get the opposite. So sine of pi over 2 is 1. Cosine of pi over 2 is 0. So this will tell me C1 equals 0 as well. So here we're done. Okay, so not so bad in terms of actually showing linear independence, but there is another method that's a bit more formulaic. So let's learn about that. So one sort of quick method for checking linear independence is by calculating something called the Wronskian, calculating the Wronskian. Sounds very fancy, you may have seen it before, which is the determinant of some matrix. Now, linear algebra is not necessarily a prerequisite, as I said before. So this is the kind of stuff you would learn in linear algebra, determinants. But we'll go through what we need. Okay, so a matrix is just an array of numbers or functions in this situation. So what we do is we take our functions, we put them at the top row of this matrix. this matrix is what's called, actually, no, sorry, the determinant of this matrix is going to be called the Wronskian. Okay, in any case, then we take derivatives. So f1 prime goes on the next line, f2 prime, fn prime, all the way down to the n minus 1th derivative for each function. And this creates a matrix. So we stick them all in this big old matrix, and then we calculate the determinant, which I'm not going to explain because it's very long to explain the determinant. We're just going to use it in a couple of situations where it's easy to do. And then we'll see what this does for us. So let's just practice calculating the Wronskian. And afterwards, I'll say how it tells us linear independence. Okay, so let's just calculate the Wronskian of sine and cosine. So I'll call sine my first function, and I'll call cosine my second function. It doesn't matter which order you put them in, but that's fine. So then, according to this, I need to calculate derivatives of each one. And I just need the first derivative of each one, because that would be n minus 1 here, since n is 2, since there's two functions. N minus 1 is 1, so I just need the first derivative. Okay, so then I stick them in this matrix. So my first function goes here, my second function goes here, then the first derivatives go underneath. And now the Wronskian, which I'll call W, is the determinant, which you write like this, there's other notations too, of that matrix. So the determinant of a 2x2 matrix is pretty simple. It comes from multiplying these two together, multiplying these two together, and then subtracting. So it's going to be sine of x times negative sine of x minus cosine of x times cosine of x. And that's it. That's the whole determinant. So now we can simplify this as negative sine squared of x, because it's sine times sine, and this is cosine squared of x. Now you might not remember this cool trig identity, but if I take out the -1, you might see it more clearly. Sine squared plus cosine squared equals 1. That's a trig identity. So this just becomes -1. Okay, so that's the Wronskian for these two functions. Let's do one more. Calculate W4. So I'll just use different names just to change things up, but it doesn't change how things work. So here are my two functions. So that means f prime of x is 4, g prime of x is 8. So then the Wronskian is the determinant of this 2x2 matrix, where I stick my two functions on top, their derivatives underneath. Then I multiply the diagonals. That gets me 32x. Subtract, multiply these diagonals, 32x, and that turns out to be 0. Okay, so where does the Wronskian come into play in terms of linear independence? Well, we just get to use this fact, which comes from another class. I'm not going to try to prove it. If W of the functions is not always 0, then you can immediately claim that they are linearly independent, which is nice. So then just to note, this is how logic works. If you do get 0, it tells you nothing. Inconclusive. And you have to try to figure out some other way of telling. Just so you're aware. So if it's not always 0, then it's linearly independent. But if it is always 0, then it's inconclusive. So I just calculated some Wronskians. So let's see if I can say anything. So this first Wronskian, is this always 0? No, not always 0. So if I look at the two functions that I took the Wronskian of, they are linearly independent because of this little fact, which we already proved earlier, actually. We proved it the long way, but this is just another way. Meanwhile, this one is always 0, so inconclusive. So you have to go and look at these two functions and prove that they're either independent or dependent some other way, the way we learned before. And in this case, these are going to be dependent if you do it like last time. It'd be like in the last video. Okay, so let's do one more example where Wronskian comes in handy because it's a little bit unclear whether they're multiples of each other, and there's only 2, so that's enough to see usually if they're dependent or independent. Okay, so 6 to the x and 6 to the x plus 2. So let's check if these are linearly independent or linearly dependent. So what I'm going to do is I'm going to calculate the Wronskian. So you might not remember how to take derivatives of things like this. Exponentials where it's not just a power of e. In that situation, you have to multiply by ln of the base and then keep it the same. So those are the derivatives. You might not remember this rule. That's okay. So now what I'm going to do is I'm going to calculate the Wronskian. Let's see what happens. So 6 to the x, 6 to the x plus 2, put their derivatives underneath. Multiply diagonally and subtract. So this is 6x ln of 6, 6 to the x plus 2 minus, oh, whoops, there should be a 6 to the x right here. Okay, minus, oh, it's the same thing, whoops. Just in a different order. But these are the same two things being subtracted, so you're 0, so it's inconclusive. So in this situation, we can't say it's independent, but we also can't say it's dependent, inconclusive. So we got to think of some other way to do it, which is the old way. Which is I just have to think about taking a linear combination of them and seeing if I can make 0 happen without cheating, or if I have to cheat and pick only zeros. So the key to this one, it's a bit tricky, is to realize that 6 to the x plus 2 is actually 6 to the x times 6 squared. And now it's easier to see that, yes, they are multiples of each other, 6 to the x and 6 to the x plus 2, because this is 36 now. So then I can take out my 6 to the x and then I can find constants C1 and C2, making this be 0 without just cheating. For example, C1 equals negative 36 and C2 equals 1 creates 0. And I was able to make 0 as a linear combination of these two functions without just picking only zeros. So that means that they are linearly dependent. Okay. All right. So So that's like the do stuff. So the stuff you like have to do, show independence and dependence. But just to sort of take things from a higher perspective for a second, just to think about the stuff we've been talking about. Like, what is all this really doing? So here's the big picture. So the idea is that linear combinations you should think about as ways to build big functions from smaller ones. Linear combinations. So for example, if I have x squared and sine of x, then I can build all sorts of functions by taking linear combinations of these two. So every choice of a and b gets me a new function. So I could build all sorts of functions from smaller pieces using linear combinations. And then the point of independence and dependence. So identifying linearly dependent functions tells us when we have an extra function that we don't need, basically, when it comes to building new things. So unnecessary in terms of like building blocks. So for example, if you have x squared sine of x and 5x squared as your building blocks, and you build up linear combinations out of these, you're actually not going to get anything different than up here. These are the same linear combinations. And that's because of this dependence of the linear dependence down here, which is that these two are linearly dependent. And so when I build linear combinations, these two pieces, these two building blocks, don't create different things. They create the same functions, just for different choices of the constants. So it's really nice when you just reduce your building blocks to their most basic pieces, and you don't have any extra pieces that are the same as what you already have. So that's the idea. So then when they are linearly independent, you get no unnecessary functions from this perspective. Okay, so that's the idea, big picture idea. Building up pieces, building up functions from smaller pieces. If you already have one type of building block, like an x squared type of building block that builds up all the x squareds, then you don't need a 5x squared because it's just building up the same things. You could just combine these two and then just use different constants to get the same functions as you would have up there. Okay. And independence tells us that you don't have to worry about that you already know that you're getting no extra functions. Okay, so that's the big picture idea. So now back to differential equations. So why all this work in a differential equations class about linear algebra? So we're just gonna take it as a big old fact. So this class is not really a proof-based class. So when you take another version of this class, then you start to prove these types of things instead of just using them. So we're just going to use it. But here it is. If you have an nth order, remember that means that there's n derivatives, linear differential equation. Oh, I guess I forgot homogeneous too. So that just means there's 0 on the right with constant coefficients. So remember, these are the types of differential equations we're trying to figure out right now. So if you have one of these, which I'll remind you, looks like this. You could use different letters than I have, but that's okay. So the homogeneous aspect is that there's a 0 on the right. The constant coefficient aspect is that these are all just numbers here, these a's, instead of other big functions of x or anything like that. And linear is just that it's in this form. Okay. So if you have an equation like this, then it always, you don't have to check every time, has n linearly independent solutions. Independent solutions. Now, I'm going to say on some interval, but I'm not going to worry too much about this interval stuff. But again, when we think of solutions, we are trying to think about intervals where the solutions actually make sense. Okay, and then, so what's interesting is that if you have like a 5th degree derivative, 5th order derivative, or 5th order differential equation like this, then it's got to have 5, these got to match. It's got to have 5 linearly independent solutions. So that's the neat part. Okay, that's what's going on. So then in fact, also any solution that you can possibly think of to the differential equation on that same interval is then a linear combination of those solutions. So then what that means is we actually have something called a general solution. So a general solution is a solution that covers all the possible solutions. And in this situation, we have that. Previously, we learned techniques and we got solutions, but we never knew if they were all the solutions or if there were some other ones hidden somewhere. Sometimes that didn't come from the technique, but this time we can be sure that we get all the solutions. So we call, I'll just call it y equals. So it'll be some linear combination of the solutions, the n linearly independent solutions. So that's what this thing is, the general solution. To the differential equation. And these y's are n linearly independent solutions. Okay, so we'll see lots of examples to see how this is not, it's a nice big fact, but it's not as complicated as it seems. Let me try to show it all at once there. So the idea is if you have something like this, then you can immediately conclude all this interesting stuff that happens. Okay, so let's see an example. So notice I haven't yet shown you how to solve something like that. We're just saying that you do have this many solutions. Okay, so here's a differential equation of the correct type. So what is it? It's a second order. It's homogeneous because it's got the 0 on the right. is linear because it's of the correct form. And it's got constant coefficients. We'll just call that CC. So how many linearly independent solutions does it have? Well, it's second order, it's of the right type, so it has 2 linearly independent solutions. So if we knew them, that'd be great because we could say a bunch of stuff. So we don't know how to find them yet, but let's just pretend we have them. So if we knew how to find them, so I will just tell you what they are for now. So they are e to the 4x and x e to the 4x. Then we could say some stuff. But first of all, we have to check if they're linearly independent to continue, because just because I got 2 solutions doesn't mean I can conclude all this stuff unless they are linearly independent solutions. So I told you they are, but let's actually check. And we can do that quickly by calculating the Wronskian. Oops. So let's do that. All right, so the Wronskian of these 2 functions would be, if I take the derivative of f of x, it's 4e to the 4x. Oops, so that goes underneath. Skip a step. And then over here is just x e to the 4x, but now I got to use the product rule, which is a bit annoying, but that's okay. Plus, okay, so you can check that with the product rule, and then the determinant is multiply the diagonals. And then subtract, and make sure it's not always 0. So I added the powers because the bases were the same when I multiplied here. And that's what happened after the minus. So then I think I'm going to get some nice cancellation. Yes, I am. These will cancel. So I just get e to the 8x. Is this always 0? No. So yes, they are linearly independent. Okay, so yes, I have 2 linearly independent solutions to this differential equation. So then I can say what the general solution is. To the differential equation is C1, so some constant times the first, plus some constant times the second, which I'll just actually write the functions in just to be clear. So this is my general solution. And general means any solution you could possibly imagine. There's no secret other solutions. They all look like this by choosing different C1s and C2s. They all the solutions are covered by this. Which we saw before, there were sometimes solutions that didn't come from the techniques automatically, but in this situation, all the solutions do come from this. And again, we're not proving it, we're just using known facts, because this is not a proof class, and it's a bit difficult, so we're gonna avoid that stuff. Okay. And I'm gonna say the interval. I'm gonna try to say it sometimes. So the interval here is -infinity to infinity, because this function is continuous and has a derivative on this whole on the whole real line. There's no like weird undefined things going on or anything like that for these 2 functions. Plug whatever you want in, it always looks nice. So that's why this time I can say the interval with confidence and not really have to worry. Okay, so let's just do a couple more examples where we do similar things like this. All right, so here are two functions. So these are both solutions to that same differential equations, which was y double prime minus 8y prime plus 16y 0, right? Yeah, that was the same equation. So these are both solutions, but do they tell you the general solution? No, because they are not linearly independent. So you got to be a little careful. So, but y equals c1 times 2e to the 4x plus c2 times 6e to the 4x is not the general solution. Because to create the general solution, you have to have two, because it's second order, linearly independent solutions. These are not linearly independent. So 2e to the 4x and 6e to the 4x are linearly dependent, so they don't tell you. So again, this is where dependence, what dependence really is saying like, oh, they're just really the same type of function. So they're not creating everything. You're missing the other piece. You're missing this xe to the, you're missing this piece completely because you're just getting two of these types instead. So you do need both pieces. Okay. So this is not the general solution because they're linearly dependent. So they cannot be used to build any other solution. They do not build all the solutions. All right, so one more example, just to apply this stuff. So if I said like, check if this is a solution, you do know how to check. So let's say check if this thing is a solution to the same differential equation. So if I ask you to check, of course, you know how to check by taking derivatives and plugging it in to see if it works, but we don't have to do that anymore because we already know the general solution. So it's not, because it's not buildable by the two functions. And so it's not a linear combination of those two, so it doesn't fit into the general solution. So it's not a linear combination of the two linearly independent solutions. So there's no way to build this thing out of these two with constants, i.e., no way to write e to the negative 5x as some amount of these first guys plus some amount of these other guys. And so why do I know that means that this is not a solution? It's because I know that the general solution covers all the solutions. So if this thing doesn't fit into that, it can't be one. So if it's not one of these linear combinations, then it can't be a solution because these linear combinations cover all possible solutions. Okay, so next time we will start actually solving these to figure out how the heck I got these answers. And it'll turn out not to be so bad, but that's it for this time. See you next time.